सर होते तिथे
म्यूट कर म्यूट कर
म्यूट करा. म्यूट कुठे करायचं?
तुमचे व्हिडिओ बंद करा. व्हिडिओ बंद कर.
Hello.
Hello.
हॅलो
Hi, Sayali.
हॅलो हाय.
Hi.
Hi.
मला विचारायचं मराठीत बोलू का इंग्लिशमध्ये बोलू, कारण मला सगळी मराठी नावं दिसतात.
So that is fine, but then we have people joining across Pan India and other locations also, and people are
Okay.
remotely connected on locations also. So we prefer to have it in English.
ओके.
We are extremely sorry. Our admin team had some internet problems, so we were not able to connect. So, but usually our session starts at 5:10, so we are more or less on time, and people are still. I can see they are joining. Just give me 2 minutes. Yes, Bharat sir, you want to say something?
No, I just want to welcome Sayu. I am Sayu. How are you? Good to see you. So I said, let me welcome all of our members who are on the today's program, and I wish all the very best to Sayu in her further career. So with this, Mangesh, you can take over.
Yeah, okay, sir. Thank you very much. So, welcome all. Though we are on a little bit late on our schedule, but we still catch up the time, and Saili will be having around 45 minutes the time whatever you require to deliver your lecture. So, welcome everyone. We have today's AstroTalk number 50. So far this is the 50th talk of Amateur Astronomers Association. So last 3 years we have been conducting this session regularly. Every month we have on second Saturday someone in the field of this astronomers, astrophysics, as well as cosmos and all those related stuff. People are coming and talking to us as well as delivering their excellent lectures. So today we have speaker Sayali Kulkarni. I guess she is from Spain right now, right? Or and she's been part of this session today, and she's actually pre-doctoral PhD researchers. She has done her MSc Astrophysics uh, and then MSc in Physics also from University of Mumbai, and she has delivered a lot of lectures related to the topic. In interest of the time, I will not talk much about it, but this lecture is about decoding the rhythms of the universe through variable stars, where we're able to learn about the different types of variable stars, particularly RR Lyrae stars, and why they are important for understanding our galaxy and all. So, With that, I would like to welcome Dr. Sayali Kulkarni to our session and would like her to take ahead this session further. Over to you, Sayali.
अं, एक सेकंड माझा
You
कॅमेरा
have,
सुरू होत नाही.
you have full rights and you can share your presentation.
कॅमेरा सुरू होत नाहीये. एक मिनिट मी ओके लेट्स जस्ट स्टार्ट विथ ओके. Can you all see my screen?
Yes, yes, we can see your full screen. Thank you.
Uh, okay, so hi all, I am Sayali Kulkarni. I am a PhD researcher. I am not a doctor yet. At Centro de Estudios de Física, this big name, which is in English, Center of Studies of Cosmic Physics in Aragon. So Aragon is a region in Teruel, in Spain, and there is a town in Aragon, like Thane district. We have this Aragon district, and we have this town in Aragon called Teruel, and I'm currently situated there. Okay, so my journey started with books, all books, astrophysics, physics, theoretical physics, especially from written by Jay Narlikar, whom I very much admire his work and his persona, his personality. Then I also read many books about Marathi, general literature, not related with science and astronomy. So yes, books were my great friends when I was a child. Then I remember my father bought me this this game called Mechanics. So from playing this game, or by playing this game, these and other games, I found out it was my teeny tiny invention for myself, that a steel needle, for example, which is not magnetic, but when it comes close to a magnet, it gets a temporary magnetism. It gets temporarily magnetized. Moreover, I also found, so I had this prism as a toy. But when I used to look through it, I could see light being separated in 7 different colors. So from that, I could derive this something. So the fact, I could understand this fact that when it rains and also there is sunlight, the sunlight is separated when they fall on the rain droplets. The light gets separated into 7 different colors, and we get to see this beautiful structure. So these were my inventions for myself. I invented this even before getting a formal education, a formal lesson about it in the school. So this is how the books, the toys, and all other stuff helped me to think. I was able to think because of this stuff. Then other activities as well. So again, when I was child, I remember that I used to go to hiking, trekking, that stuff. So when I used to go for hiking, trekking, rappelling, climb, this kind of used to do these activities. So we used to go for camping. We used to do these activities, adventurous activities in the daytime, and in the night time we also used to have sky parties. So this is the time where I got introduced to the sky, the actual stars, the concept of constellations, and that stuff. So all this stuff, all these activities, reading, trekking, hiking, sky parties, playing games, these activities made me curious about the universe around us. They made me able to ask questions to the surrounding. Then cut to the bachelor's and master's. So I did my bachelor's and master's, both degrees in physics from University of Mumbai, where I learned all this physics subtopics like mathematical physics, magnetism, nuclear and atomic physics, wave mechanics, general and special relativity theories, electronics, and this stuff. These subjects that I learned in during my these 2 degrees, they again made me provided me food for my brain. Moreover, they acted as foundation to do my further career, further research in astrophysics. Then, after my master's degree from University of Mumbai, I got involved in a citizen science project where we used to analyze radio galaxies through GMRT. If you know, GMRT is giant meter wave radio telescopes. We used to download the data in FITS format, FITS file format. This is format of the files of the data, and then we used to classify the radio galaxies. So for those who don't know, radio galaxies are there. When you look at their optical counterpart, they are simply boring elliptical galaxies. But when you look to them through radio telescopes, you can see beautiful structures. Some galaxies have I don't know, the flows, and some have AGNs. So AGNs are, in short, so for in almost every galaxy, there is at the center of it is a black hole, right? So the black hole is sometimes active, means it accretes matter around itself, and the matter around the black hole gets ignited at some point. So this is called somewhat AGN. Well, I'm not trying to define AGN, but give some idea for those who don't know. So while doing this project with my fellows, we found that galaxies are but many galaxies travel in the space in clusters. Also, galaxies have black holes at their centers. So when galaxies evolve, they don't evolve individually. However, this evolution is always codependent. The evolution of the black hole, evolution of the galaxy, and its cluster, which it belongs to, they kind of correlated and they co-evolve. So we also carried out a project called Black Hole Galaxy Galaxy and Galaxy Cluster Co-evolution through GMRT for the upcoming, then it was upcoming, and now it's almost here, SKA observatory, that era. Moving on, I also involved myself in various astronomy outreach activities. Like I used to work as an astronomy outreach officer and head of the resources at a mobile planetarium, where we used to inflate it. There was a setup of a 360-degree camera, sorry, not a camera, a projector inside, and where there used to we used to have these astronomical shows, and my job was to narrate those shows, take up the question answer sessions, and we used to visit different schools in Mumbai, in Bangalore, in Goa, and we used to conduct these shows, take up the question answer sessions, and there was a lot of astronomy science discussion. And I found out that students are curious, of course, but teachers, principals, parents are more curious about it, because they are the ones who have to handle all these questions throughout the day. They have to survive these questions coming from their children and students. So they were more curious about astronomy and how to, how these things work, how the universe works, to know this. I also, I still write, well, I started writing something from the age of, 4 or 5 or 6. So I have been writing from the age of 6, and I have this a couple of snapshots from my write-ups. So whenever I write, I cover various themes, various topics, not just from astronomy, but from general physics as well, general science as well. For example, this snapshot, this article here talks about why the sky is blue, where I explain to general audience how the relay scattering and the relay scattering and the Raman effect. Where here this second snapshot here this article deals with the general science and pseudoscience. So it describes what is the difference between the science and pseudoscience. So likewise, like this, I have written many articles, and there are 2 novels I'm writing. They are in pipeline. Both of them are science fiction, sci-fi novels. Well, I would like to mention here that whenever I used to read Dr. Jayan Naralikar's books, those were not just about scientific facts, but those were about science fiction as well. So I think somewhere by reading those books, this I don't know, the flame was ignited in my mind that okay, I also want to write something. So I just pursued my passion for writing and passion for writing for general audience, general readers. Okay, so after spending 4 or 5 years after my first master's degree, getting involved myself in various astronomy outreach and writing stuff, I joined University of Potsdam for another master's degree, where I learned many things. So our syllabus, I remember, had many topics, many subjects, right from Big Bang, cosmology, to stars and stellar physics and exoplanets, and all. Of course, most part of our, the master's degree was dedicated to Python. So whatever you see, whatever you learn, you go to some, you download certain data set regarding it, and you use a language, any language of your choice. I chose Python. You can choose any language of your choice if you're liking, to analyze that data, reproduce some results, maybe invent new things, model the data, and so on. I also, well, during those 4 years of master's degree, I also attended a couple of conferences where I presented some work, not a bigger deal, but my teeny tiny work in front of the audience, and I was so happy about it. Then I I started my student job at Leibniz Institute of Astrophysics in Potsdam. It's called AIP. So, as a student assistant to an astrophysicist over there, I analyzed weather data, especially wind parameters, and I tried to use some machine learning techniques to predict the wind parameters. So the wind parameters, but this was for astronomical purposes. That means I downloaded the data from a weather station at Cerro Paranal in Chile. So we have in Chile, we have many telescopes. So my job was to predict the wind parameters for like 2 months, 2 years, 20 years, and so on. So that it will help the astronomers or astrophysicists or the observers at the observatory to manage their timetable. So, for example, if the wind is rough, the night is rough, the winds are high, super high, then at that night they would not simply open the dome of their optical astronomical observatory, so that there will be, so that they can save their money, their research time, and other resources. So this is how my job was to predict, the winds, the weather in general for the next, I don't know, 10 years, 20 years or something. Then I also took up I took up master's thesis, which was about evolution of young star clusters in the Hubble space. So there is this legacy extragalactic UV survey of Hubble Space Telescope, and my job was to download that data surveyed by the legacy extragalactic UV survey, means LEGUS, from the Hubble Space Telescope in near ultraviolet, blue, I think visible or visual, and infrared, those 5 passbands, and look at their, or study their evolution, means formation, evolution, and dispersion. So for those again who don't know, star clusters. So stars, most of the stars, or many stars, they are born in clusters. Then the clusters evolve. The stars also evolve along with the clusters, and then eventually they disperse, because some stars die and get faint. So my conclusions from this study was that the star clusters are usually short-lived. Star clusters do form and disperse very quickly in galaxies with high stellar masses and high stellar formation rates. And the third conclusion, well, not a conclusion, but just a comment, that if our sun were a part of a cluster, it would have a shorter lifespan. Means the Earth wouldn't have been existed. We wouldn't be having this conversation if the sun was part of the cluster, because the stars who are the part of the clusters, they form, they evolve, and they die very quickly, rather than field stars or lone stars. So we are lucky that our sun is not a part of the cluster. Okay. So this is a graphic. Please take a moment to read this, and if you have any question, please go ahead, ask me. Then I can continue the presentation.
Yes, you are telling I'm Makaran Moghe.
Yes.
So I'm asking you, there is one question you told over here in the previous slide, that our sun would die, okay, in a very short span, right? If it would be a part of the cluster, isn't it?
Yes.
So what is the reason for it?
Yes, the reason is because the short distances. So, the closest star to our sun is Proxima Centauri, right? It's like four-ish light years away. But my intuition is, if the sun was part of a cluster, if it is inside a cluster, then this distance would have been very, very less, right? Sometimes, in some cases, it is so less, or even during their birth, means their formation, many stars get formed as binary stars, right? So this binary interaction is very, very important in evolution of a star. So in the binary star system, one star literally snatches the matter of another star and gets massive. So this massive star it lives its life quickly, and it dies faster than this low mass star, right? So if there was this situation that our sun is part of a cluster, and also it had a companion, then I don't know. Yes, our sun would have lived its life faster than whatever it is having.
Yes, there must be some process, no, by which it is happening. Because in normal course, if it is any isolated star is there, so in what way that isolated star will die? Depending on its mass, definitely.
Mass.
It is going to become a white dwarf or a neutron star or a black hole, or we can say that bursting of star. Okay, what do you call that one as a nova or supernova. So this is applicable for the isolated star, right? If the same star is found in the cluster, then how it would behave exactly? Because of which it dies very quickly. Quickly in the sense what, of course, in that particular time span.
Right.
So there must be some reason over there. So what exactly is happening within the center of that particular star? So because of which the whole stuff gets collapsed. There must be some process.
Right. Yes. So good question. So one cluster gets if it gets interacted. So we are all of us are under the influence of the black hole at the center of the Milky Way galaxy, right? So it is spinning. I don't know if it is spinning or not, but we are spinning. We are spinning at this so we are orbiting the center of the galaxy, all of us. So if a star is a part of a cluster, and this cluster, when orbiting around the center of the galaxy, when they interact, even if it slightly interacts with another cluster, then due to tidal forces, these clusters get dispersed. So even earlier I mentioned that galactic cluster and the black hole are codependent. The evolution is codependent. Likewise, a star, its cluster, if it has a cluster, its cluster, the center of the cluster, because the clusters are a group of stars which are gravitationally bound towards its center. So
that is true.
Yes. So if the cluster has a lot of gas and the star formation is happening because it has gas, the cluster has gas, then the overall star formation and dying process is faster. If there is a massive star which becomes a supernova, then the gas is expelled out of the cluster, and that's how the cluster gets dispersed. And at that time, if it gets dispersed, then at that time, the stars, these lone wolves, get some time to breathe. That means to live more. This is how it is. It is complicated process, not too complicated, but this is how this works. Yes.
Okay. Thank you.
Okay. Thank you. Thank you for the question. Can I continue?
Yes, you can continue.
Yes, if no one has a question, then yeah. Okay, then after the master's, PhD. PhD I got at the Centro de Estudios de Física del Cosmos de Aragón, in CEFCA. So here we use Javalambre, means it is actually Javalambre, but in Spanish the Z is pronounced as K. So it's Javalambre's Astronomical Observatory at a mountain not too far away from Teruel. So where I started working on variable stars. So variable stars, especially the RR Lyrae subtype. There are many other types of variable stars such as Cepheids, Mira or Myra variables, and so on. But I'm working on RR Lyrae especially. So RR Lyrae stars, they pulsate in their size, which is translated into variation in their brightness at regular time intervals. So RR Lyrae stars. So this is a kind of map of the stars according to their, let's say, age and evolutionary stage, for those who don't know. But for those who know this scientific jargon, this is a CMD, means color magnitude diagram of a globular cluster, a star is in a globular cluster. All right. So all stars burn their hydrogen in their center. This is called main sequence. Our sun is somewhere here. I don't know. When the stars run out of their hydrogen, when that means the hydrogen is converted to helium, they leave their main sequence. Can you see this point? This is called turn-off point. The hydrogen stops burning, and now helium kind of starts burning, and then they enter into red giant branch, where they get inflated. But after the red giant branch, somewhere in between, they kind of have this premium stage where it is called as horizontal branch stars, and RR Lyrae variables stand here, are located here. So in this premium or prime location or prime evolutionary stage, the whole stars gets expanded. When it gets expanded, it gets less bright, and after some time, it gets again contracted or contracted. Its size gets smaller, little bit smaller, and then at that time it gets more luminous, not luminous, more bright. So if we try to look at their brightness, we get something called light curve, means it is a wave. Here their brightness gets, means here at this point, they are getting bigger, expanding. That's why their brightness is little bit less. Now they are into this contraction or this stage. They are now contracting, and now they are contracted. Their sizes are smaller, and they get brighter. So it is like timtimana, like twinkling of the stars, but not due to the atmosphere of the Earth. But here the twinkling, this kind of, in general language, the twinkling is because of their internal mechanism. We can, study this twinkling or this changes in brightness, their brightness in these wave-like structures called light curves, where on the x-axis we have phases, and on the y-axis we have magnitudes, which are again brightness in different bands, optical bands. Here we use G, R, and I broadbands, which are common with the SDSS, the Slow and Digital Sky Survey, GRI, and we also have JVARs. Our surveys, our observatories narrow bands. So in total there are 1, 2, 3 broadbands and 4 narrow bands. So I have submitted my research paper on this, and it will soon be published. So to make the light curve, we have magnitudes on the y-axis, and phases come from time and period, where the time in Julian or modified Julian days come from the Gaia survey, and the periods come from, the time comes from our survey, which is called as JVAR survey. Z stands for Havalambre, the observatory's name, and VAR means variability. So Havalambre variability survey. And these are the pass bands. So the period comes from the RR Lyrae catalog of the Gaia DR3 survey, and time in modified Julian days come from we have retrieved from this JVAR survey, and then now we retrieve periods. We took periods from the Gaia survey, but we want to refine these periods and check those periods by ourselves. So what do you mean by period? So period is period of the variation. Means whenever a star through its expansion and contraction completes one cycle, which is translated as magnitude, change in magnitude, that is called periods. So what we used SDSs, means slow and digital sky surveys templates. Templates are just models, empirical models. We fitted those templates, and there is this package, Python package of this fitting of the templates, and those template package returns this visual data, plus it returns a set of periods, new periods. So now we know now we have two different sets of periods, one coming from Gaia survey, one is ours. That means it is my research. Well, they don't the difference is not too much, but still we are refining the period, and that's what we have achieved in this research. So while doing this research, I also presented about this my research in many conferences. So one of those conferences was on Cepheid and RR Lyrae variable stars in Morocco in November 2024. Now let's come to general astronomy and astrophysics, where how modern observational astronomy has evolved from analog photographic plates to digital CCD sensors, and now into machine learning and artificial intelligence. So senior researchers, people here might remember that they use these glass plates to take the observations. So the first revolution was when astronomy went digital, that is from the glass plates to CCDs. So before CCDs, it was so there were astronomers with those they captured the sky on photographic plates, which was a slow, inefficient method, and it was difficult to measure fainter objects or many objects at the same time. Then came the CCDs. CCDs are the silicon sensors. They collect the photons. The photons release the electrons inside pixels, and then electrons, those pixels means electrons in those pixels convert the light patterns into numbers and numbers into digital images. So this is how CCDs revolutionize astronomical observations. The impact, because of the advent of CCDs, the telescopes, the telescope cameras, for example, Hubble Space Telescope wide field camera, are now more sensitive. The observations are faster and precise and much more deeper. So to give you an example, my survey, means the Havalambre survey, is deeper than 21 magnitude. That means there are many fainter objects because they are fainter because they are either far away from us, or there is a lot of dust and gases which are obscuring the light coming from them, and a lot of stuff. So because of this, many objects are fainter, and because of the CCDs, the cameras that are using CCDs installed on telescopes, we can observe those images. So we can see an image of a Horsehead Nebula. Senior people, again, they may remember that in their times, the Horsehead Nebula, this image was not this clear. It was not as clear as this, right? The second revolution was when machines learn to think. Because of the CCDs and all this stuff, advent of all this new technology, we have a lot of data. What to do about this data? We have millions of galaxy images, stellar lights, exoplanets, AGNs, so on. It would take many years for humans to analyze this data. So with the help of AI, which scans this data in the form of number and saves it in the form of numbers and images, and then it defines correlations among parameters which a normal human cannot do. AI also can predict the unknown parameters. For example, so I'm right now dealing with a sample of about 50,000 RR Lyrae stars retrieved from the Gaia dataset, Gaia survey. So I know metallicity. Metallicity means amount of iron present on the star with respect to the amount of hydrogen. This is called metallicity, or in general, well, ion abundance, but ion abundance for many of the stars can be used as a proxy to the metallicity. So, from the spectroscopy, I know the metallicity, these numbers for 10,000 stars only. But what about the remaining 40,000 stars? So what I will do here, I will use some machine learning algorithm to predict the metallicity in the remaining 40,000 stars. How? Let me go back a few slides. So what I will do, I will input these light curves of with this 50,000 RR Lyrae star, a sample of 50,000 RR Lyrae stars to my machine. It will look at the shape of the light curve, and it will somehow correlate the shape of the light curve, the hidden trends in it. Also, I will also input the metallicity numbers known for the known metallicity numbers for those 10,000 stars as a test sample. What machine will do? It will find the trends between the light curve shapes and a lot of other stuff. It will also considers these numbers of metallicity, and then it will predict the metallicity for the remaining 40,000 stars. So as an output, I have metallicity numbers, metallicities for for my entire sample of 50,000 stars. So this is how AI can help me do my research. Moreover, modern surveys such as Gaia, ESA, Astron, and SDSS, Chandra discover millions of objects every day. So there is a lot of information. AI filters this torrent because not everything is an astronomical object, but most of it is just noise. So AI filters out first this torrent of alerts, helping astronomers rapidly identify, estimate this data, identify and classify this data or whatever the images we have received into different objects such as supernovae, optical counterparts of gravitational waves, AGNs, or all that stuff, nova and supernova again. Yes. So finally, the latest generation of AI models can combine images and spectra. They can uncover hidden relationships. They can accelerate new galaxies. Also, they can summarize the literature. They can help arrange a conference. So AIs are not just helping us do science, but they are also helping us to do other things related to science, for example, a conference. And also they can help make a presentation like this one. To end the story with the next decade, I think the next decade is about observatory like Vera C. Rubin, which will produce a lot of data again in catalogs of for over 20 billion galaxies. Humans alone cannot analyze this data, so they will sure need an AI. It will help astronomers discover exoplanets, decode the exoplanet atmospheres, map dark matter, which is a very hot topic in astrophysics, detect cosmic explosions, and uncover the unexpected. So I think this was all about the astronomy and astrophysics that I know. And thank you.
Thank you, Sayali. That was really a wonderful lecture, knowing more about the variable stars and how you help them to decode the universe. That's really a great stuff, and I would say the amount of data what you would be analyzing, it would be enormous. So, everyone, we have open for the question answer sessions. If anybody has any question, please raise the hand. Anyone want to ask question or discuss about the journey what Sayali has started with her own personal journey about being from a student to educator to be now a scientist, or I would say researcher. That was really a great journey. I mean, everybody would definitely look forward to know more about how I want to perceive the same kind of journey or something like that. So question answer sessions are open.
AI tools, are they ready-made or you have developed?
Which tools?
Artificial intelligence tools, machine learning tools, you have developed, you have written the program or they are ready-made available?
No, they are readily available. There are many packages that you can
Okay.
easily download and do
Mhm.
some coding.
Okay.
Again, for coding and how to incorporate those packages, you can take help from AI like Claude and ChatGPT,
Okay.
and they can help you write a code. So even that barrier between you and the data analysis is now, there is no barrier, of course, because so I learned this Python coding during my masters, but not everyone has this opportunity to learn and to practice coding. But yeah, AI has now resolved that problem too.
Okay.
So we have one question from one of our school students where he is asking like how these variable stars could be observed uh, through the normal telescope. Is it possible to do and track them or something like that?
I don't think normal telescope means or telescope in your backyard. I don't think so, because the normal telescope that we use during sky parties is not that sensitive. It doesn't have that resolution power. These stars are surveyed, observed. So if you look at the star just one time, you can see the star but cannot capture its variability, because it will be in that certain phase when you look at it. So you have to survey that star again and again and again and again. So that's why we have surveys, not just telescopes. So what they do is, with this band pass, different bands they have, that they have, again not just optical, but some infrared, some UV too. They scan that certain sky patch again, one night, two nights, second, third night, 4 nights, 11 nights. So that's how you can capture the variability. If you look at it just one time, you can see just again, it's not possible to resolve a star because they are very far away. Most stars, most RR Lyrae stars, well, you can see that their evolutionary stage. They have left their main sequence. They left their RG phase even. So they obviously are very far away from us. Mostly they are located in the globular clusters around the galaxy. So globular clusters are again the group of stars, but which are very compact. They're strongly gravitationally bound. So to look at the star from a telescope that you have in your backyard, backyard, is not as simple as it sounds. So you
So basically, the duration of observation is quite big,
Hmm.
not one night or something like that.
Not one. Yes.
Consistently, you have to
They're
observe.
far away from us. They're very
Yeah,
far away from
very
us.
far.
We are barely we are barely could resolve a cluster, each and every star from a cluster. We even don't know, many clusters are still unresolved. Many structures are still unresolved, which are at the center of the galaxy, our galaxy. Let alone the other galaxies, even we are not able to decode our galaxy fully. So it's not possible.
Right. Vijay, you have any question? Vijay, Jitesh, Rajiv, Makran, any of you have any question? You want to say about the session, what we had today? Add your comments.
The session is good one. After all, she is my student. She was my student when she
I'm
was
still
doing
your
her
student.
UG, but still we have to do a lot of analysis of the data, isn't it? But physically, it is really possible or not? I do not know, because from the data, are we able to construct any, we can say, empirical formula? I do not know about it. But if we are able to do it, isn't it? What will be the possibility? What will come to know from that particular empirical formula? Are we able to do that? Can we construct that empirical formula from the data? Just like what we are doing in
Yes.
nuclear physics. Okay, that Geiger-Nuttall
Yes.
law is a empirical formula of alpha particle decay. So in the same manner, so we are having a lot of data about this RR Lyrae variable star. So from that one, are we able to construct any empirical formula?
Yes. So I know some researchers. Sorry. Please continue.
No. Anybody has done that job or not?
Yes. So these templates that you saw, they are taken from, there is a stripe, a part or area of the Milky Way galaxy called stripe 82. So this researcher, Cesar, whose name is Cesar, he installed a lot of data. Then he used some technique, some machine learning. I don't remember at the moment. He used machine learning technique, some algorithm that can derive this empirical relation between a light curve shape and the template. Template means a model, a visual model.
Okay.
Yeah? Difference. Yes. So from it, he he hasn't mentioned that empirical relation, but he has this visual representation of that empirical formula, which in the form of this template. So what this template is based on. So I'm doing currently this template construction of templates. So earlier I used pre-constructed templates. Now I'm kind of into reconstructing those templates from the sample of RR Lyrae stars. So what I'm doing is your favorite Fourier decomposition. So yes. So from from the parameters of the Fourier decomposition, from the I think there are some ratios. They can give you the amplitude of the RR Lyrae stars. Amplitudes. Now, right now we just have magnitudes, but we can also refine the amplitudes. And then there are certain ratios in the parameters from this Fourier decomposition that can help determine this empirical relation. It can also help us refine or determine the metallicity relation from the shape of the light curve of a RR Lyrae star. So by just looking at the shape of the light curve, it can determine the AI, the machine learning kind of thing, that those algorithms can determine the subtype of star. What is subtype of star? So the stars, some stars they fluctuate or variate in fundamental mode. These are called RRAB subtype stars. RRAB Lyrae stars. Other stars, they variate, means expand and contract in first overtone. Simple wave mechanics, first overtone. They're called RRC Lyrae, RRC subtype stars. And then there are other type, the third type, which is a combination of fundamental mode and first overtone.
Achha.
So these three subtypes have different light curve shapes. RRC subtype, the ones having this variation frequency in first overtone, have sine waves. The light curves have simple sine waves. However, RRAB subtype stars have sawtooth with rapid inclination and gradual declination. Something, the sawtooth kind of RR lines. So the machine learning, or sometimes humans cannot visually bifurcate or differentiate between these shapes and that stuff. Also, there's light curves. Some light curves are not, a smooth sine wave. For example, there is a bump, small bump. This is called Blaschko effect. because on the during this fluctuation, this variation in the size, there is a shock wave. Shock wave is emerged from the center, something like that. We are not able to fully decode that, decipher that, but this is something called Blaschko effect. So this Blaschko effect, this shock wave kind of stuff, is translated into this bump, a teeny tiny bump on a rather smooth light curve. We cannot sometimes miss it. Humans can miss it, but AI does not. The machine does not miss it. So yeah, so this is one of Fourier decomposition is one of the methods to determine the empirical relation. Another method, again, I'm not doing Fourier decomposition of EJ. My codes are doing it. The packages that I'm using are doing it. Another is PCA. It is called PCA, means principal component analysis. So we have multi-dimensional data. Dimensions are not just a visual, but they are, the information is dimension. Dimension is information. So even a color of the star is another dimension. So what this method, principal component analysis, does is it reduces the dimensions. These dimensions are reduced into simple 2-dimensional or 3-dimensional, maybe 4-dimensional data. Again, dimensions are here not spatial dimensions. Dimension is simply information. So it reduces the dimensions and give you curves, visually curves that so a set of curves, let's say 4 or 5 or 6, and then you can decide, or not us, again the machine again decide which curve fits the an individual star's light curve the best.
Okay.
And then
Means, does it mean like this, that you collect the data and you plot the curves, and from the curves you can construct the empirical formula? Is it going to happen like this way? Means these are the steps to be followed like this way?
Yes, but the stars are all, the data is already been collected. That has already been collected from the survey. So survey is going on. So there is this main survey called J+, Havalambre's photometric local universe this survey. But so this is deals with optical and little bit UV, little bit infrared.
Yes.
It has 12 band passes. But whenever the night is rough, it is not suitable for the optical observations whenever there are clouds and all. So we use this Havalambre's variability survey. It gets activated, and it kind of again looks at scans the sky, part of the sky for those nights, and captures the variability, and then it saves the data. Yeah. And I just get the data, retrieve the data from the web page, our survey's web page.
Okay.
Yeah.
Fine. It's nice to understand.
Yeah, I think there is one question where you are working from Spain, but then we saw that Vera Rubin is also being observatory, which looks promising, scanning the sky or surveying the sky, and I think that will be also very useful tool in near future. Will fully functional for studying the variable stars. So you want to put some thought around that?
Sorry, I really have very very little idea about Vera C. Rubin. I will get an idea about it when so there is this upcoming conference in September on LSST, Vera C. Rubin legacy, or not legacy, the time survey data, which I'm going to attain and present my work there. So our idea is to construct the templates depending on the sample of RR Lyrae stars that we have, and we want to see if we can use those templates on the way this time series data coming from the Vera C. Rubin. So after I have attended the conference, I have discussed and met with other stars, scientists, then I will be able to comment. Or
so maybe the season 2 of your lecture would be something around that.
Again.
Just wanted to add, like you talk about data and all the things. So is this data accessible to the general people or amateurs, people who can contribute to this thing, and how they could contribute?
Yes.
I mean, you some reference point where basically the audience what we have is schools, college students who would like to contribute or maybe try out some experimental or some variable. Like I remember a couple of years back, we did a practical session on observing the algol. Though it is not a purely variable kind eclipsing binary, it is or eclipsing variable. So we tried because the period, what as you said rightly, that it could not be observed in one night, but at least in every 3 days it changes its intensity or magnitude because of the eclipsing binary. So we tried doing that, but because of the atmospheric this thing we were not, but still we were able to do some kind of observation around that. So something like that we would like to see from an amateur astronomer perspective, where people can.
Means if it is, Mangesh sir, if it is possible for us to construct such kind of a say lux meter, with the help of which we can measure the intensity of light, and if we are able to attach that particular meter with our optical telescope, so
Right.
we may be able to what you can say record that particular change which is taking place in the intensity of light. What do you think?
Yes, definitely. So that is what we tried to do it. I mean, in recent times, even I think Ayuka had conducted some workshop on variable stars also about our students very recently. I mean, couple of months back.
Acha.
Thanks. I mean, that's
Good evening, ma'am.
yeah, Vijay. Good evening. Good evening.
Very nice to talk to you, ma'am. Sayali Kulkarni, madam. Very proud to talk to you.
Thank you.
Can you enlighten about aliens, madam? There are so many messages coming from the space. So, according to research knowledge, can you elaborate that?
Messages.
Yes, madam. Are they really in reality like that?
I'm not sure. I cannot comment on that because I don't know what kind of messages you're talking about. So.
I mean,
Yeah, there are so many messages from the space about so many talking about the aliens. Are they existing, madam?
We cannot say that aliens don't exist. At the same time, we cannot say aliens do exist. We are not sure. But considering the tremendous amount of, the distances and the tremendous amount of energy that is required to travel from one place to another place in space, I don't think even if we are able to receive something, kind of alien, a message from alien, I don't think we will be able to meet at any point. At any point in time.
Okay.
Yes.
Vijay sir, shall I tell you something about it?
Yeah, sure.
yeah, please. Go.
Actually, no. There is a Drake-Sagan equation is there. Okay, it's a product of probabilities. Nearly 6 to 7 probabilities are there. Okay, and with the help of which we can predict whether there is another life or not in the space. Okay, so if we go through that one, you will come to know the probability becomes so small, 0 point many zeros, and then last one somewhere else that is coming. So at least means as on today, we cannot say about its existence. Okay, means even if it exists, so one of the probability is there that what is the probability that still that life exists, means though that life is sending some messages over here, because whatever the information we are getting from the space is through the light only, and the speed of light is not infinite, it is still limited, though it is quite greater, but still it is limited. So we are getting information from the distant stars. Okay, that is also very late, isn't it? So at this moment, we cannot say that really the life exists over there or not.
Yes.
So it's a Drake-Sagan equation. You will come to know from that whether the life exists or not, other than Earth. Means, do we have any neighbor?
Makaran sir, very simple thing we can think about today's real life example is that we have sent 50 years ago one spacecraft which is at the edge of the solar system.
Right.
Even at the speed of light, to communicate it now at point in time requires 1 day to communicate it, almost 24 hours
Correct.
to send the message and receive
Right.
back the response about it. So
Yes.
it is still, from an astronomical point, it's still very near to us, but from our day-to-day experience, it is very far for us, like 50
Correct.
years to reach that point. So, I mean, at astronomical level, it is something which looks like, oh, we are very close, but at a astronomical level, they are very, very far away.
Far away. Right.
Okay, any
Yeah.
else want to
Yes.
add contribute? Yes,
Yeah,
sir.
yes, AI can make mistakes. How do you ensure that they are not making mistakes and your decisions are correct?
Means AI can make mistakes. Sure.
Yeah.
So sometimes it gives you a result, a positive result when there is no result. So it is called as false positive.
Mm-hmm.
So for every, well, I'm not like expert in AI, then that kind of, those algorithms, but whatever I have learned so far is for every algorithm there is a confusion matrix. There is something called confusion matrix. So I think there is one algorithm. I don't remember the name of that method, but it comes with this confusion matrix. It kind of gives you false positives, uh, like it can give you a percentage of error it is making. So even if it is, even if you are not using AI, just simple coding, simple human, human typed Python coding or anything, Java or anything, it automatically comes with the percentage of error it is making in the whole analysis. So there is always room for errors. So, for example, when I fit the templates, mean those curves to the light curves, there are some points that they don't fall exactly, not don't fall on this curve, means they are not fitted by the curve. Those are called residuals. So in that case, we also calculate or measure and visualize, means make a plot of those residuals. Those residuals tell us how far those points are from the fit line. And as a researcher on the variability and variability, through Fourier decomposition, I also check the residuals for each and every star, and I look at the residuals if it has some trend. If it does have some trend, then something is going on.
Okay.
So errors. This is how we calculate not errors but the uncertainty in our analysis, and we use the same uncertainty to clear up the data more and reanalyze the stuff. This is called bootstrapping. So you do something, you get percentage of errors, and along with the uncertainty and error bars, you use those errors again to reanalyze the thing, and this goes on until the error bars are beyond some ratio, not ratio, some knee value or some acceptable value. 0.05 is okay, but 5 not okay, something like that.
Okay. How much time it takes for computer to process all this data?
It depends on what method you're using. So when I'm trying to do this principal component analysis thing for my this entire sample, this sample of RR Lyrae star, it took 40 hours.
40 hours. Okay.
For two consecutive nights, my laptop was on. It was analyzing. It was doing this fitting stuff.
If you can analyze on laptop also, you can analyze data on laptop.
Yes, sure. Yes. Laptop, desktop. Desktop is more preferred device to use, but yeah, the laptops are always.
Okay.
You can carry them anywhere. So even I can keep one loop going on, and I carry it in my through international airports and flights and that kind of. Yeah.
So data is in gigabytes or megabytes?
Mine is pretty much. It has pretty much low number of objects, so it is like in megabytes.
Okay.
But yes, as I said, the galaxy stuff is more complicated because galaxies are huge, and that they're complicated systems. So I have seen my colleagues dealing with petabyte, not petabyte, yeah, something similar amount of the data.
Okay.
Okay. Anyone has any question? Bharat sir, you want to conclude? You want to add something to the session? Bharat sir?
I have a small query for Sayali. The query is like this. Does it mean that amateur astronomers cannot do any variable star work?
They can do. Yes. Yes. So, have you heard about something called Zooniverse?
Yeah.
Zooniverse. Yeah.
Yes, yes.
So yes, there are many citizen science projects. It's like Zooniverse and so on. That they give you visual data to analyze. No, okay. If you want more, complicated data like not visual, but just a few lines of codes can decode it, then yes, sure, you can go, you can visit any web page of any telescope, just read a bit literature about it. Uh, you now don't have to deal with these things. You just open ChatGPT or Claude and ask it. Just ask, what should I do to do this? It will tell you step by step. It will explain you. Again, thanks to AI, even that barrier has been destroyed, destructed. That now no one has, even a student living or based in a remote place, where there are, he or she has less number of resources. He or she has, just a Wi-Fi and a good laptop. They can start doing analysis on their own.
No, my query is like this. Uh, One has a telescope. Now the problem is, excuse me, one has a telescope, and also there are now available cameras also which can be attached to a telescope, and one can also start doing actual photometry of the stars. So I had a small query for you. Is Are we going to continue having observers to actually observe the variable stars? I am aware of AVSO where they actually ask people to do their own observation and then look for the variability and also look for other features. Does it happen at uh, amateur levels? However, in India, very few people are into variable stars. But can we propagate variable star observation by using the telescopes? Because there are now more number of telescopes available in city like Mumbai and others, and they go out of the station to photograph the sky. So can we give them these kind of projects for looking at variables?
Well, I don't know about actual this telescope and photometric the observation thing, but so if one has a telescope so strong that it can resolve a globular cluster far away from the Earth, and it can resolve each and every stars in the globular cluster, which is another hard thing, which cannot be. I don't think it can be done through a human eye, no matter how strong, how sensitive a telescope is. It will sure need some photography. Also, it will need some another technique called PSF photography, point source function, something that photography. So I'm not expert in PSF photometry, not photography, sorry, photometry. But it kind of uses this this method uses kind of this slit, photometric slit with different sizes, starting from 0.01, I don't know, micrometer or something, 01, to resolve each and every star in at a distant location, distant position. Uh, Long story short, we cannot totally rely on a telescope that you're talking about. We need space telescopes for this, because observing for an amateur astronomer, they can observe, sure, they can observe the local sky, but for deeper sky, fainter objects, and also to avoid the atmospheric, barrier, which kind of cancels most of the light coming from the outer space, we need space telescopes. We cannot simply rely on ground telescopes or just telescopes in our backyard, installed in our backyards. So, for example, the survey we are using is a ground telescope. it is located in an observatory. It is mounted in an observatory, Havalambre Observatory. It has a 2.5 meter radius, right? But still we cannot fully rely on it. We have to use this Gaia data. Gaia data, ZTF means Wiki Transient Telescope, ZT Transient Telescopes, that those observations, then AAVSO observations. So what we do is we cross match those two catalogs. So catalog means data from this ground survey and another catalog from the space survey, so that we can be sure that okay, what we are seeing is actually the RR Lyrae stars, actually a variable star, because there is no atmosphere, just eating up your information, majority of the information in between you. So there is no one between you and your observation. So we confirm, we only take up those stars or those variable stars in particular which have been bona fide, which have been confirmed from the sky surface. So this is how it works. So Earth's atmosphere, so distances is major hurdle or a condition. Then obscurity, the atmosphere, Earth's atmosphere is another one. Then the dust between the cosmic dust and gases, this is the third one. And there are a lot of things that can, that may give you problems with the observation. So yeah, so I think I hope this answers your question.
Good. Anybody has any other question, or we are good to conclude today's session? We have already reached 6:25 p.m. So if we do not have any other questions, so Sayali, thank you very much. That was really a great session on decoding part, knowing more about the variable stars and learning from it and how it can be helpful. We'll continue to learn more about it, and definitely we look forward from you to maybe upcoming session with more about the information about where are we going in the near future. So all that from amateur astronomers. We thank you very much and all the best for future endeavors and sessions. Thank you very much for today.
Thank you.
Thank you. Thank you. All the best.
Thank you.
Bye bye. See you.
Okay, bye bye.
Bye.
All the best.